Hello and welcome again to my Physical Science Online Video Lecture Supplement series. Today's video I'm going to be working through some examples to go with the lecture notes that are prepared for the Chapter 2, which is on kinematics and the description of motion. And so before we begin with that, I think it's worth maybe reviewing a few of the important equations that come out of this chapter. There were a few more this time than the last time. In fact, in the last chapter there was really only one actual equation, which was the density equation. This time there are several. This top one is giving the average speed, and it is the distance traveled divided by the time. The distance that an object travels starting from rest under acceleration is given by this equation. D is the distance, A is the acceleration, T is the amount of time for which it accelerates. The assumption is that the object started from rest. If you drop an object, this is an application of that previous equation. The specific acceleration that you have is g, the free fall acceleration, 9.80 meters per second squared. The acceleration can be determined by determining the change in speed divided by the time over which that change occurred. That is the constant acceleration equation. That's also valid for finding an average acceleration in general. The final speed, if you have a constant acceleration, can be determined based on the initial speed v0 plus the acceleration times the time. And finally, if you have an object which is moving in a circular motion, then the centripetal acceleration for that object is the speed squared divided by the radius of the circle about which the object is moving. So with that said, let's proceed to the example. In our first example, we have a car which drives 3 kilometers in 5 minutes, and what we want to know is what is the average speed in meters per second. So recall that to find the average speed, you can use the distance traveled and divide it by the time to travel that distance. So this is from our notes on speed. Distance is the actual path length traveled. In this case, we're told a specific distance, and then the time we're also told. So in this case, the distance traveled is 3 kilometers, the time is 5 minutes. So our equation was basically average speed equals distance traveled over time to travel the distance. That's v bar equals d over t. And so what we basically need here is the distance which is traveled. So that would represent this, be represented by this 3 kilometers. So d is 3 kilometers. T is 5 minutes. So we basically can write V is 3 kilometers divided by 5 minutes. And so you throw that into your calculator, what you end up getting is 0.6 kilometers per minute. Now, the thing is that this example asks specifically for the speed in meters per second. So we need to convert this into meters per second. So if you are watching this because you're an online student, for example, you know that when you take a quiz, the questions are going to typically ask for what is the speed in meters per second. So you've got to be able to sort of imagine that the answer says something like the speed is blank meters per second. So you can't just put 0.6 as your answer, because that is not the correct answer if we want it in meters per second. So what we got to do is convert from kilometers to meters. So remember that kilo means 1,000. So there's 1,000 meters per 1 kilometer. And then we have to convert from minutes into seconds. So 1 minute is equal to 60 seconds. So now we need to do some multiplying and dividing. So you have 0.6 times 1,000, and then that it has to be divided by 60. You can see that the answer is going to be 10. So the answer is that the average speed is about 10 meters per second. So 10 meters per second. So in this little box we would write 10. So the next example says that the Soviet Luna 1 probe needed 36 hours to get to the moon from the Earth, and it traveled at an average speed of 10,500 kilometers per hour. So what is the distance that it had to travel in order to get from the Earth to the moon? So we have that the average speed is the distance divided by the time. What that basically means is that we can do some rearranging here. So if you have distance over time is equal to average speed, you can then multiply both sides by time. And so you see this side will cancel out. You're left with distance is equal to average speed times time. So that would be 10,500 kilometers per hour. And then that's going to be multiplied by 36 hours. So we need to basically multiply these two numbers together. 10,500, and that's times 36. That gives you 378,000 kilometers, excuse me. And of course, it's possible that we may want to put this answer in meters instead. So you can multiply that by 1,000 meters per kilometer and end up with 378 million meters. So that's how far from the Earth to the moon. It turns out, by the way, that there is slightly more to it than just that number for the distance, that the moon is in more or less an elliptical orbit around the Earth. So the distance is variable, but that is roughly what the correct average distance is. For our next example, we consider a car which is going to drive 3 blocks to the north, then 2 blocks to the west, then another block south, and finally 2 blocks east. And so the question is, how far has the car driven? And also, what is its displacement? So to understand the difference between the how far has it driven and what's the displacement, it's worth looking in our notes again. There's this nice little diagram that shows displacement and distance. So imagine that the car starts here and ends here. The displacement basically is a line that starts where the car started and ends where the car ends, a single straight line. It has some magnitude, which is essentially the length of this line in this case, and then there's also a direction. So in this case it's basically northeast. You can be a little more specific by measuring, for example, how far east of north is it? That is, what angle between the north and the displacement vector. So that's displacement. If you want the distance, then you basically have to measure out how far this path length actually is. So this would be equivalent to looking at the odometer when you started and looking at the odometer when you stopped and seeing how many miles were added to the odometer. Assuming, of course, that you don't pull off or anything like that. Even if you do pull off the road, you could still add that to the total distance traveled. This path length kind of makes it look like you never actually pull off the road though. So distance is just how much is your odometer going to increase by. Displacement is, you could think of it as when you're standing here at your destination, how far away and in which direction are you from where you started from. So one way that we have of doing this is imagining that the car starts somewhere. We'll call it here, for example. and what happens is that it goes 3 blocks to the north. So 3 blocks to the north, maybe it looks like 1 block, 2 blocks, and then 3 blocks to the north. Then it says 2 blocks to the west. So we go 1, 2 to the west. Then it says go a block south, so 1 south, then 2 blocks east. 1, 2. That may look like kind of a silly path to take, but if you imagine this car going in a downtown area where there maybe are lots of one-way streets, this maybe makes some more sense. He's actually trying to get to here. He has to come up here to where the one-way street allows him to go this way. Then he comes down here. Then he can go this way on the other one-way street. So the question is, how far total has he traveled? And then also, what is the displacement? Well, in this case, the displacement would represent the distance and direction from here straight up. Oops, it's hard for me to draw stuff straight on the setup that I've got, but straight up to here. And you can see that in this case it's 2 blocks to the north. So displacement in this case is equal to 2 blocks and then maybe due north. On the other hand, if we wanted to figure out the distance, we could count how many blocks he's traveled. So 1, 2, 3, 4, 5, 6, 7, 8. So the distance traveled in this case is equal to 8 blocks. Notice that it doesn't have any particular direction because distance is a scalar and therefore there is no direction associated with it. As a continuation of that question, it says, what if each of these blocks is 50 meters long? And let's say that the driver needed 1.5 minutes, 1.0 minutes, 1.0 minutes, and 1.5 minutes to complete each step of the trip described above. So what was the car's average speed and what was the average velocity? Alright, so now to determine what the average speed was, what we have to do is use that the speed is equal to the distance divided by the time to travel that distance. Since we've already used that equation, I'm not going to go back to the notes to show where this is coming from. So the total distance in this case is 8 blocks times 50 meters per block. And the total time in this case is 1.5 minutes plus 1.0 minutes plus 1.0 minutes plus 1.5 minutes. So this, if you multiply 8 by 50, you get 400. So it's 400 meters divided by 1.5 plus 1 is 2.5, plus 1 is 3.5, plus 1.5 is 5. So 5.0 minutes. So the speed in this case is going to be 400 divided by 5, which you can see since 8 times 50 was 400, then 80 times 5 is also 400. So the answer to this must be 80 meters per minute. And then we could even convert this into meters per second by basically multiplying to get rid of the minutes, 1 minute over 60 seconds. And so you end up with 80 divided by 60. So 80 divided by 60, or 8 over 6, will give you the same answer, namely 1 1/3. So with two significant figures, assuming that somehow you know that this has 2, you'd put 1.3. So 1.3 meters per second. All right, so that is the average speed. What about the average velocity? Well, to get to the average velocity, what you have to do is that you need to use the displacement rather than the distance. So the average velocity, and you can put a little bar over it to represent an average, is the displacement per unit time. So we've already figured out that the time is 5 minutes. The displacement in this case is 2 blocks times 50 meters per block to the north. So that divided by 5.0 minutes. So you know that 2 times 50 is 100. So you would have 100 blocks per 5 minutes. And 100 blocks per 5 minutes is, or excuse me, 100 meters per 5 minutes is also the same thing as 20 meters per minute. So your average velocity here is 20 meters per minute, and then you can convert that again by multiplying through by 1 minute per 60 seconds. So 20 divided by 60 is a third, so you'd end up with 0.33 meters per second. Doggone traffic. All right, now we ask, going back to this question of the moon orbiting around the Earth, basically the average distance that this moon is going to have from the Earth is 384,000 kilometers. But this distance actually varies because this is an elliptical orbit. So here it's very close to the Earth relative to here where it's farther away. And in fact, the closest to the Earth might be over here. And this point over here is called the perigee. And this point over here that's farthest away is called the apogee. And it turns out that at this farthest point, this apogee, there's a 406,000 kilometer distance between Earth and Moon. And at perigee, it's a 363,000 kilometer distance. And so if, for simplicity, we take the Earth to be stationary, how far is it from perigee to apogee? So to solve this problem, we can draw a diagram of the Earth and of the Moon, which is orbiting the Earth. So the Moon is here, then sometime later the Moon is over here. And basically what we've been given are the distances between the Earth and the Moon. And so we're told that this distance right here, from shortest distance between Earth and Moon, is 363,000 kilometers. And then we're likewise told that this distance from center of Earth to Moon at greatest distance is more like 406,000 kilometers. So the question here ends up being, how far apart are they from least distance to greatest distance? So this right here would be the magnitude of displacement, which I'm just going to label as x. So magnitude of the Moon's displacement we can label as x. And to get x, you can add these two numbers together because they are exactly opposed from each other. In other words, this is a straight line from here to here along these numbers. And so x in this case is 363,000 kilometers plus 406 6,000 kilometers. So if you add those two numbers together, what you end up getting is that this distance is about 769,000 kilometers, or if you convert it to meters, 769 million meters. So that is the displacement between perigee and apogee for the moon if the Earth is stationary. If the Earth is moving, which it is, then this gets to be a bit more complicated, but I'm not going to try and work that example today. Okay, the other part of this example, or the logical extension of this example, is to ask, how far does the moon actually travel in moving from perigee to apogee? In other words, when it moves from here around this path to here, how far does it travel? From here around the path to here. And actually, the moon's orbit is more appropriately from here around the path to here. In any case, you get the same answer. And it turns out that this is not quite so easy a question as it would appear. And the reason for that is that the moon's orbit is not circular, it is elliptical. So from this point traveling around the curve to this point, what you actually have is half of the total perimeter of the ellipse. So you have to know how to find the perimeter of an ellipse. It turns out that that is not so simple. There's a number of different formulas that you can use to approximate it algebraically. One is to use this approximation. Perimeter is approximately 2 pi square root a squared plus b squared over 2, where a is called the semi-major axis. It's the distance from, for example, the perigee to the very center, or from the apogee to the very center. Remember that the Earth is actually at one of the focal points, not at the center of the ellipse. B, on the other hand, is the distance between basically center and semi-minor axis. So B is basically the minimum distance across the ellipse. A is the maximum distance across the ellipse. So this formula works reasonably well. It should get you an answer within about 5%. This formula is slightly better in that it will be a little more accurate for computing the perimeter. I'm going to go ahead and use the easier formula and call it close enough. So in this problem we have been given, basically we're going to use the formula that the distance traveled is 1/2 of the perimeter, which means that it is 1/2 of 2 pi square root a squared plus b squared over 2. So you can see that there is a half here and there's a 2 here, so there's a little bit of cancellation. So we have right here the value for the semi-major axis, b. That's given in the problem because it says assume the semi-minor length b is equal to the average Earth-Moon distance. So this is the semi-minor axis length. We need to get the semi-major axis length. So the semi-major axis length is basically like this. So we'll call A to be this distance and also must be equal to this distance. So in other words, A is half of the value of that magnitude of displacement that we found in the previous example. So A is equal to 1/2 of x, and so that is equal to 1/2 of 769,000 kilometers. And so if you take 769,000, 769,000, you divide it by 2, what you end up with is 384,500. So the value for x is also very nearly equal to, or the value for a is very nearly equal to this average value. And so that tells us that it's actually a fairly circular ellipse. So that's good because this formula is valid for an ellipse that is very nearly circular. So we have 384,500 kilometers for A. So D is going to be equal to pi times the square root of 384,500 kilometers squared plus 384,000 kilometers squared. And then you also need to over square root 2. By the way, if we throw everything under the square root sign, then there's an over 2 here. By the way, one way of checking to make sure this formula makes sense before I plug all the numbers in is to ask, what would happen if this ellipse was turned into exactly a circle? Well, in that case, a and b would be equal. So a squared plus b squared would become, and I'll write this in black because it's kind of a little bit of an aside. You'd have a squared plus b squared would be equal to a squared plus a squared. So that's 2a squared. So if you have that divided by 2, what do you end up with? Well, the 2's cancel here. And if you take a square root of all that, then what you end up with is square root of a squared, which is equal to a. And so you'd be saying half the perimeter is pi times a. Well, a in this case just represents the radius of the circle. So half the perimeter is pi times r. That means that the whole perimeter is 2 pi times r. And that's what you'd expect for a circle. So that's how you know that this is a reasonably valid approximation. Okay, so let's plug in numbers for what we actually have here. What we actually have here is d is equal to pi times the square root of, and so now we're going to have to take this number that we just found and square it. So we end up with this number. And then to that we're going to need to add another 384,000, and that actually also needs to be squared. So you get a number like this, then you divide it by 2, you get a number like this, and then you take a square root, you get a number like this. 384,250. It's almost exactly the average of 384,000 and 384,500 for what that's worth. So that then needs to be multiplied by pi, and what you get is this number. So now we go back to the question of significant figures. How many significant figures do we have? Well, assuming that all these numbers are just rounded to the nearest thousand, there are 3 significant figures. So we would need to round this to, looking at this number, we would have 1,210,000. So I'm not going to put the big number in here because there's a lot of digits to write. Call it big number. And what the final ends up being is 1,210,000 kilometers. So that is the actual distance traveled as opposed to the displacement between one and the other. For our next example, we have a car, and the car begins at rest and accelerates to a speed of 20 meters per second in a time of 5 seconds. And so it wants to know, what is the car's average acceleration? So looking in our notes, what acceleration is defined as is basically the change in velocity. And so if you speed up, slow down, or change direction, you have an acceleration. And the more the change is, the greater the acceleration, or the more the change in the same amount of time, or the faster the change, the quicker the change, whatever you want to call it, the greater the acceleration will be. So acceleration actually is the time rate of change of velocity. So what is the acceleration actually given by? Well, average acceleration is change in velocity divided by time for the change to occur in. So we can also call that change in speed per unit time if the car is moving only in one dimension. In other words, as long as there's no turning or direction changes, then its change in speed per unit time is sufficient. For velocity, you could also say that if the car is initially moving from left to right, and then suddenly at the end it's moving from right to left, then initially it has a positive velocity and finally it has a negative velocity. So in any case, this right here is the equation that we need in words, and here it is in symbols. So the one that we're actually going to use, the equation we're actually going to use, average acceleration is change in velocity divided by time to make that change. We basically need this one, final minus initial divided by time. So here is the time, 5 seconds. This right here is actually the final speed, v final. And since it begins at rest, this is saying that the initial speed is 0. So the average acceleration we can get by taking 20 meters per second minus 0 meters per second and dividing by 5 seconds. So this part is already 0, goes away. 20 divided by 5 is 4. So the average acceleration in this case, 4.00 meters per second squared. So that is your average acceleration for the car. Okay, after this happens, the car slows to a speed of 10 meters per second in 5 seconds. So we want to know what the average acceleration is for that interval, and also what the average acceleration for the entire 10-second motion would be. So we can maybe call the acceleration in the second interval of time, the second 5 seconds, that is, as maybe A2, and the one we found before is A1. And then for the entire time, we could call it just A. So how are we going to find each of those? Well, A2 we can get by using the final speed, 10 meters per second. This is V final 2. Would be 10.0 meters per second minus the initial speed in that interval, which is actually 20.0 meters per second. And then we divide the whole thing by 5 seconds. So what do we get for that? Well, we're going to end up with negative 10 meters per second divided by 5 seconds. And so that's negative 2.00 meters per second squared. Okay, if we want to find the average for the entire interval, what do we do? Well, you may be tempted to say the average for the entire interval is this plus this divided by 2. And if you were to do that, you'd have 4 minus 2, which is actually a positive 2. Then divide that by 2, you'd end up with 1. However, that is not the correct way of doing this. To get the average for the entire interval, you take with the initial speed for the entire interval. So this is V naught. And you end with the final speed for the entire interval. And you subtract the two from each other. So you have 10.0 meters per second minus the initial 0.0 meters per second. And then you divide by the amount of time. In this case, you're going to end up with the same answer. And the reason why you end up with the same answer is because this process is basically constant for a while, then constant for another while, and both things happen for the same amount of time. So this is going to end up as 1.00 meters per second squared. However, consider what would have happened if we, for example, allowed the car to slow to a speed of 0 meters per second in the second 5 seconds. But instead of making it 5 seconds, maybe we make it 10 seconds. So what would the average have been in that case? Well, then this upper one here would be 4. This one right here would again be -2. If you add the two together straight up, you'd get 1, but if you did the whole interval, you start at rest, you end at rest, that means the average actually should be 0. So you have to basically go with what was your initial speed or velocity, what was your final speed or velocity, take the difference, divide by the total time, and that's how you get the total acceleration. All right, our next example shows us a graph. And the graph has position on the y-axis and it has time on the x-axis. And it asks, what are the units which would go with the slope of position versus time? And the answer is, for one thing, don't just look at this graph because this is showing a velocity and a distance. To find the slope, you always take the rise, you divide by the run. So if the rise is a distance or a position and the run is a time, seconds, then the slope of that has to be distance or meters divided by time, seconds. So the slope would be meters per second. On a similar vein, if you want to have velocity or speed on this axis and time on the x-axis, then the slope is going to be meters per second divided by seconds, which would be meters per second squared. So notice what these units correspond to. The slope of distance versus time was meters per second. Well, that's the unit that goes with speed. The slope of speed versus time was meters per second squared. That's the unit that goes with acceleration. So that means that the slope of distance versus time graph is actually telling you something about how fast the object is traveling. The slope of speed versus time graph is telling you something about the object's acceleration. So now let's consider another example. This time we drop a ball from the roof of a building and we try to measure the speed every half second on the way down. So initially it has a speed of 0 because it's being dropped, and then after the first half second it's going at 4.9 meters per second. After the next half second it's at 9.8 meters per second, and after the next half second 14.7 meters per second. So the question is, how fast will the speed be after 2 seconds? Well, remember what I just said on the previous example about slopes here. Slope of position versus time gives speed or velocity. Slope of speed versus time gives magnitude of the acceleration. So one thing we could do here, since we have 3 different numbers to work with, is make a little graph of these. So step 1 is going to be make a graph. Now I can sketch a graph here, but I think it would be better to make this graph on some graph paper or using a graphing program. So let's go ahead and do it using some graph paper. So here's our graph paper. We're going to need to basically come up with a scale to go with this graph. So this graph could be basically a speed versus time for a ball, for dropped ball. So this axis right here would be the speed in meters per second. This is the time in seconds. So every half second, so 1/2, 2/2, 3/2, 4/2 would be off. So maybe the half seconds could be these increments. So 1.0 seconds, this one right here would be 2.0, and so on. And then along this axis, we need to have these distances. So 5, 10, 15, for example. 5.0 or 5, 10, and 15. And so at half a second, we're basically at 5. At 1 second, we're just a little shy of 10. At 1.5 seconds, we're just a little more shy of 15. And what you would do here is then you'd need to make a line of best fit for this. I don't have a way of putting a ruler out to do that. Once we've drawn our line of best fit, we have to pick a couple points that are on the line of best fit, and just from eyeballing it, there might be a point like 0, 0, and then up here maybe there's a point like whatever is halfway between these, 1.75 seconds comma 17.5 meters per second or whatever. And so you'd go slope, which we represent with an M, is rise over run. So that's 17.5 meters per second minus 0 meters per second divided by 1.75 meters per second minus 0, this is just seconds, minus 0 seconds. So you'd have 17.5 meters per second over 1.75 seconds, or 10 meters per second squared. So that's giving you the acceleration. Now, I'm limited here by the piece of graph paper that I'm using and by my ability to draw a straight line without actually being able to use a ruler on my screen. So the next best thing to do would be to make this line up in Excel. Turns out if you did that, what you'll find is that the slope is actually 9.8 meters per second squared, which not coincidentally happens to be the free fall acceleration. So this is within about 2%. So the actual slope in this case is 9.8 meters per second squared. So that corresponds to the acceleration. And so the equation that we would use then, v is equal to v naught plus a times t. That's one of the equations we reviewed at the very beginning of this video. It's dropped from rest, and it also says initially it has a speed of 0 meters per second. So v is equal to a times t, that's 9.8 meters per second squared, times the time, which is 2.0 seconds. If you multiply those together, you get v equals 19.6 meters per second squared. If you tried to predict that from the line that I drew, you'd end up with 20 meters per second squared. That's not too horribly far off. So for our next example, we drop a golf ball from a helicopter, kind of like this guy's doing. And the helicopter is 49 meters above the ground. And so the question is, how long does it take for the ball to reach the ground, assuming that there's minimal air resistance? So this basically is going to make use of the fact that when you have an object which is falling, it has a constant acceleration of 9.8 meters per second squared. That's assuming that you're falling near the surface of the Earth with negligible air resistance. And so basically the object speeds up, speeds up, speeds up. Also means it travels a greater distance for each second that it falls. And so the distance that a dropped object travels is given by d equals 1/2 gt squared. That means distance is half of that 9.8 meters per second squared free fall acceleration times whatever time it falls for squared. So we're making use of this equation right here. Distance is 1/2 free fall acceleration times time squared. Or in other words, d is equal to 1/2 of gt squared. The thing that we're trying to solve for, how long does it take for the ball to reach the ground, that is actually t. This thing is 49 meters above the ground, so that is our value for d. And of course, g is 9.8 meters per second squared is the free fall acceleration. So we want to find the time. That means we've got to rearrange this equation. So if you have 1/2 gt squared is equal to d, you can divide both sides of that by 1/2 of g. And what that gives you is that t squared is equal to 2d over g. So to get rid of the t squared, we take a square root of both sides. And what you're left with is that t is equal to square root 2d over g. So now we can plug some numbers in. The time is going to be 2 times 49 meters divided by 9.8 meters per second squared. So that means that the time is going to be given by, let's go ahead and get our calculator out. So we have 2 times 49, it's going to be 98, divided by 9.8 should give us 10. So now we take the square root of that, which is here, and that gives us 3.162 seconds. So we'll call it 3.2 seconds because there's two significant figures given up here for d. So because d was given as 49 meters, t is approximately 3.2 seconds. So the follow-up question for that is, what is the speed of the ball in the above example just before impact? So how fast is it going right before it hits the ground? Well, this is basically the same question that we had earlier about the rock being dropped from a certain height and then figuring out how fast it is after 2 seconds. Now we're figuring out how fast does this thing travel after 3.2 seconds. And it turns out the acceleration is even the same. So for this next example, how fast, we use v final is v initial plus at, and again it's being dropped, so we're saying this is 0 because that's what happens when you drop something. Dropped means the initial speed is 0. T we solved for over here was 3.2 seconds, and so the final speed is 9.8 meters per second squared times 3.2 seconds. So let's pull open the calculator. Since this is the time from before, we can just multiply this by 9.8. And what you end up getting is 30.99, which rounds off to 31. So that means that the final speed right before hitting the ground is about 31 meters per second. So there's the answer to the second, there's the answer to the first of those pair of examples. That brings me to another pair of examples. This one also makes use of the free fall acceleration, and what we have here is a bullet being shot straight into the air. This is not exactly straight in the air. Maybe if it was pointed vertically, it'd be straight in the air. In any case, it's being shot straight up into the air with an initial speed of 294 meters per second. The question is, how high is this bullet going to go before stopping? And then how much time does it take to get to that height, and how much time before it hits the ground? So that's quite a few questions. This is a fairly complex looking example, and so there are several steps in order to solve it. It kind of hinges around the following points. First of all, the acceleration is, in this case, the gravitational acceleration or free fall acceleration, 9.8 meters per second squared. Okay, so that's stated. This right here represents the initial speed, so this would be v naught. And so we can use an equation that looks something like this. Distance to get to top is equal to 1/2 of the free fall acceleration times the time squared minus the initial speed times the time. It's actually a plus here, but in reality this is a negative acceleration. So that's one way of solving it. The trick is that you got to know something about the time. And the time is given by basically solving for when is it that the final speed is 0, because the speed at any given time, the final speed, is the initial speed plus the acceleration times time. So if we take for this thing right here to be 0, then we can get the time that it takes to get to the top. And so t, rearranging this equation, is v naught over g. It's negative v naught over g. So that would be negative 294 meters per second divided by negative 9.8 meters per second squared. So pull up the calculator. Since there's two minuses, I'm not going to bother with the signs because they cancel. So 294 divided by 9.8 gives us 30. So this is saying that the time to get to the top is 30 seconds. So that's 30 seconds to get to top. That actually answers part B. So part A, then, we would need to plug in the 30 seconds here, and so you'd end up with d is equal to 1/2 of negative 9.8 meters per second squared times 30 seconds plus 294 meters per second, this part squared, times 30 seconds. So let's plug those guys in. So we had 30, we'll go ahead and square it, we'll multiply it by 9.8, make sure that's a negative, then we multiply that by 1/2. So divided by 2. So for this first part, we'd have d is equal to negative 4,410 meters, and then to that we're going to add so plus, we'll go ahead and put this in parentheses, 30 times 294. So that's 8,820, and if we add them you get 4,410. So 8,820 meters, when you add them, 4,410 meters. That's how high up this thing is going to go. So that leaves us with one question. How much time until this guy hits the ground? Well, it takes it 30 seconds to get to the top. It turns out it's going to take it another 30 seconds to get to the bottom. But we can show that without having to to just state, oh, it's going to take the same amount of time, because we have our equation here. So this equation basically says d is equal to 1/2 gt squared plus v0t. And what we're going to do here is we're going to say on the way down, this part is 0 because it reaches the top, it stops, then it comes down. And so we have 4,410 meters is equal to 1/2 of, in this case, the acceleration is in the same direction as the thing is traveling. So we have plus 9.8 meters per second squared times time squared. And so the time squared in this case, 4,410 meters times 2, because we're dividing by a half, divided by 9.8 meters per second squared. So the time squared, if we pull open the calculator, so we need to multiply by 2, we need to divide by 9.8, you get 900. If you take a square root of that, you get 30. So time squared was 900 seconds squared. Time is 30 seconds. So 30 seconds to get to top, 30 seconds to get back to bottom. Total time in air, therefore, is 30 plus 30, or 60 seconds. And so that answers everything on that example. What we've done here is essentially make use of this fact that you have an object which is initially moving, that is, the bullet has an initial upward velocity, and it has a uniform acceleration. And so in order to figure out how far the bullet travels in a given amount of time, what we do is we combine the equation for distance traveled versus time with constant speed, and we combine that with the distance versus time for constant acceleration that started at rest, in other words, starting with 0 speed. And so that combination gives you that the distance is 1/2 of the acceleration times the time squared plus the initial speed times the time. So a follow-up question to that is to ask what the velocity and what the position of the bullet is going to be 10 seconds after being shot from the gun. Now you know that at 10 seconds after being shot from the gun, it hasn't traveled for the 30 seconds it takes to get to the top of the motion. So what that means is that the velocity is going to be in the upward direction at that point. So let's figure out what the actual magnitude of the velocity is. That is, how fast is it going? What is its speed? And then we can also figure out how high above the position of the pistol this bullet is. So again, we're going to be making use of this equation that finds the final velocity is equal to the initial velocity plus the acceleration times the time, bearing in mind that because the initial velocity and the acceleration are in opposite directions, if this is positive, then this has to be negative and vice versa. So basically what we have is that the final speed is equal to the initial speed plus the acceleration times time. That is the initial speed plus gravitational acceleration times time. And so that's 294 meters per second plus, again, they're in opposite directions, so this is actually a negative 9.8 meters per second squared times 10.0 seconds. So this quantity right here is negative 98 meters per second squared. And so your final speed, or the magnitude of your speed, is basically going to be 294 minus 98 in meters per second. So you can see that 294 minus 98 is going to be just shy of 100. It's going to be just shy of 200. So it'll be 196 by the time all is said and done. So this is 196 meters per second, and if we want direction, it's traveling, whoops, it's not a very well written word, traveling up. Okay, so that solves for the velocity v final. The position that we're looking for we could call x final or d final, and we make use again of that equation that combines an initial velocity with an acceleration. That is, we're making use now of this equation, d equals 1/2 at squared plus v naught t. Again, because this and this are in opposite directions, this gets a negative sign with it. So we have d is equal to 1/2 at squared plus v naught t. And so that's 1/2 of negative 9.8 meters per second squared times the time, in this case 10 seconds squared. And then this is negative, note, and then to that we add 294 meters per second, the initial speed, times the time, 10 seconds. So this quantity right here is 2,940 meters per second times seconds, so 2,940 meters. This quantity right here, we'd have half of negative 9.8 is negative 4.9. Okay, that times 10 times 10. So 4.9 times 10 is 49, times another 10 is 490. So we have negative 490 meters here. So the total distance is going to be this 490 negative plus 2,910. So you get 2,420. So the total distance is 2,420 meters. So that is how far above, and this right here is how fast it's traveling at this point in time.